In this video, I want to solve this problem. It will be a quick problem. I have a differential equation with the presence of a Dirac delta, and at the same time, you also have these boundary conditions that the function g of 0, which is continuous, is equal to 0 at 0, at x equal to 0, and at x equal to 1. So g of 0 is equal to g of 1, which is equal to 0. So how do we solve this problem? Well, first we have to understand the role of this Dirac delta. Once we understand the role of this Dirac delta, everything will be quite easy if you know the theory of ordinary differential equations, because this is actually an ordinary differential equation once you, let's say, take into consideration the role of the Dirac delta and throw it out of the window, let's say. So you can understand that the Dirac delta is equal to 0 almost everywhere except at x equal to 1/2. So basically, this differential equation is almost coincident with the following differential equation, where this is equal to 0. And this is true everywhere, almost everywhere, except at x equal to 1/2. So this is just the intuition. But how do we take into account the presence of the Dirac delta? Well, I will assume that you are perfectly aware of the properties of the Dirac delta, and what I'm going to do is I'm going to integrate both sides of this differential equation from 0 to xi, and I have to specify what xi is, but xi, you can think of it as just a real number which can take the values from 0 to 1, and we have to differentiate between the two possibilities, that xi is smaller than 1/2 and xi is greater than 1/2. But first things first, so if we integrate this equation from 0 to xi, what we get? Well, if you think about it, this second derivative will give us the first derivative, g prime of xi minus g prime evaluated at 0. So that's the integral from 0 to xi of this second derivative. Then, of course, we have the integral from 0 to xi of g of x dx. And then we have to integrate the Dirac delta. But when you integrate the Dirac delta, if the Dirac delta is not included in the interval of integration, you will get 0. Otherwise, you will get 1. So if xi is greater than 1/2, you will get 1 because the Dirac delta belongs to the interval that you are integrating over. And otherwise, it is just 0 because if the peak of the Dirac delta is outside the interval of integration, assuming that it's this one, well, you get 0 because there is nothing here. And we can put all these conditions together, these two conditions together, and I can say, okay, so this is equal to theta, which is the step function of xi minus 1/2. But this basically means that this is equal to 0 if xi is smaller than 1/2, and it is equal to 1 if xi is greater than 1/2. Now, I will not take into consideration what happens when we, let's say, assume that xi is equal to 1/2, because the step function, I mean, it is discontinuous at the point xi equal to 1/2. It is possible to extend its definition and to give a value to theta of 0. And when xi equal to 1/2, we have theta of 1/2 minus 1/2, which is theta of 0. So one can give a value to this, but actually we're not interested in that here, because that's just a discontinuity for the first derivative of the function g. And how can I see that easily? Well, you can see that, for example, if you evaluate this equation at xi equal to 1/2 plus, so this means that you are taking the limit as xi goes to 1/2 from the right. And then similarly, you can also calculate this equation when xi is equal to 1/2 minus. And of course, that's the limit as xi goes to 1/2 from the left, so 1/2 minus. And if you take those two equations and you subtract them, you can quite easily get to the following equation. You have something like g prime evaluated at 1/2 plus minus g prime evaluated at 1/2 minus, and you can understand that this g prime of 0 will get cancelled because it will be equal, I mean it will be the same in both equations. So once you subtract them, this will cancel. And similarly, you can understand that this integral will also cancel. If you want to be, let's say, nitpicky, you have something like the integral from 1/2 minus to 1/2 plus g of x dx. But since g of x is continuous, this integral does not have any surprise, does not yield an infinite result, so it will give 0 actually. So you can easily understand that this will give us 0 because g of x is continuous and the integral of that will be a continuous function. So if you take the difference between the integral, which is some function f of x plus a constant if you want, but you have to evaluate it between 1/2 minus and 1/2 plus. And once you do that, you will get 0 because f of x is continuous. So this is what you get, and you also get plus 1 here. Why? Well, because when you evaluate this theta function at 1/2 plus, you will get 1. Whereas when you evaluate it at 1/2 minus, you will get 0, right? Due to the definition of the theta function. Simple as that. So this is the condition that we can impose. Let me cancel this integral. So I will cancel this integral here. And here I have 1. This is an important condition. Another condition that we have to impose is the following. G of 1/2 plus is equal to G of 1/2 minus, because G is continuous. So here's two conditions, and then we have another two conditions from here. So we have to impose G of 0 equal to 0 and G of 1 equal to 1. Now we can consider two intervals. The interval from 0 to, let's use x in this case, x between 0 and 1/2. In this case, I mean the differential equation, since we are not considering 1/2, we are excluding that, is simply g double prime of x minus g of x equal to 0. So I'm using the double prime instead of this second derivative symbol. This is a simple ordinary differential equation which gives us something of the following form. G of x can be written in the following fashion. A e to the x plus b e to the minus x. Similarly, when we are in the interval 1/2 and 1, we have the same equation, but now we have to be careful because we have these conditions to impose, which means that these constants here will be different. So we have g of x equal to c e of x plus d e of minus x. So now we can impose the conditions. We have the first condition, and let's assume that the first condition is this one, the second condition is this one, then the third condition will be this, and the fourth condition will be this. So the first condition, g of 0 equal to 0, we have to use this equation, and we have to set x equal to 0, so we have a plus b equal to 0. Then we have the second condition, which is g of 1 equal to 1, so we have c times e plus d times e to the minus 1 equal to 0. So g of 1 equal to 0. Then we have the third condition. So we have g prime evaluated at 1/2 plus, but when we evaluate the function, I mean, when we calculate the derivative of the function at 1/2 plus, we have to consider this equation here. So we have c times e to the 1/2. So when we take the limit, we can put 1/2 here because this function is continuous at 1/2. So instead of writing 1/2 plus, we have just 1/2. Then we have plus d times the derivative of this. So we get a minus because we have minus e to the minus x. Let's put a minus e to the minus 1/2. So if we evaluate it at 1/2, then we have to subtract g prime at 1/2 minus. So 1/2 minus must be considered in this interval here. So we have to take the derivative of this. So you have a e to the 1/2 minus, due to the derivative, b e to the minus 1/2. And this should be set equal to 1, like this. Then we have the fourth condition, which is the continuity of the function g at 1/2, this one. So this is a simple condition which tells us that c e to the 1/2 plus d e to the minus 1/2 should be equal, or if you want, we can put the minus and this should be equal to 0. We have a e to the 1/2 plus b e to the minus 1/2. Just like this. Now, this is just a simple system where you have the unknowns a, b, c, and d. If you want, you can solve these two first. For example, you can solve for b equal to minus a, and then here you can solve for d, which is equal to minus e squared times c, and then you can substitute them below in the two equations below, and then you have a linear system which is easy to solve. I will give you the solutions. So we have c equal to 1/2 e to the minus 1/2 minus e to the 1/2 divided by e squared minus 1. Then from c you can calculate a, which is 1/2 e to the minus 1/2 plus c. So you have this here. And then you can use d equal to minus e squared c. From here you can calculate d as well. And then from a and c you can calculate b, which is equal to minus a. So to give you just the intuition behind these coefficients, I have prepared a MATLAB script where I have defined the 4 coefficients here. I have considered an interval from 0 to 1 with 10,000 points. So I'm going to discretize the interval from 0 to 1 with these points, this number of points. Then I define the function here, y1 and y2. So y1 will be the function in the interval from 0 to 1/2, and then I have the function y2, which is defined in the interval from 1/2 to 1. And then I put them together, I draw the plot, and also I plot the derivative, which is discretized with this code here. So I will not get into the details of the code, but if I run the code, this is the function g of x that we call g of x in the problem. You can see that g of x is equal to 0 at the boundary, as expected. So g of 0 is equal to 0, g of 1 is equal to 0. And then you can see that it is continuous at g of 0.5, which is g of 1/2. It is continuous and it has a value around 0.23, something like that. You can see from this graph that there is no continuity in the derivative because of this sharp edge that you have at 0.5. Indeed, when you take a look at the derivative, you have something like this. So the derivative is continuous everywhere except at 0.5, which you can see contains this jump, and the jump is the value of this derivative minus the value of this derivative here. So um, on the left of 0.5 you have something like 0.5 in the derivative, and then on the right of 0.5 of x equal to 0.5 the function, the derivative is around minus 0.5. So the difference is indeed 1. And even if I discretize the derivative, you can see that the calculation is still quite correct, quite precise. And that's it.